Hi, so this is going to be a review video for lecture 2, which covers measurements, accuracy and precision, observations, prefixes, sig figs, all that good stuff. So we're going to start by talking about accuracy versus precision. And with accuracy, we're talking about how close the measured values are. So with accuracy and precision, we're talking about measurements. And if we imagine these both as kind of like a dartboard, with accuracy, we're talking about how close the average is to center. So if I have a bunch of different measurements that go around, remember that our center point is this one. And again, it'll be over here. But with accuracy, we're looking for a center point or an average that's really close to our center point. For this class, we say that's about plus or minus 1% off from the actual measured value. Well, the actual value, because what we've measured is what we're measuring, and we're trying to find out how accurate it is. With precision, we're talking about how close the different measurements or values are to each other. So this would be kind of similar to, for example, if I try to bake a cake like 8 times, and every single time I do the exact same thing wrong, I'm not accurate, I haven't made a cake. Let's say, for example, I switch the salt and sugar every single time. So I wouldn't be accurate. I have not made a cake. I haven't made a good cake, but I am very precise. I have done the same thing, and I have created the same thing. They're all grouped closely. So this would be if you had, for example, if our measured values were like 20.2, 20.1, 20.3, 20.2, 20.2, 20.3. And we could have a situation where we have the happy medium, where we had a situation that was both precise and accurate. That is the goal. That's the gold standard. We would like to be both precise and accurate. But that doesn't always happen because we're humans. We make mistakes when we're measuring. We have tools that are calibrated improperly. We have a lot of different issues that crop up that can all cause a bad measurement. So another example, so let's say that for all of these examples, our true value is supposed to be 25.0. Maybe for our accuracy, we have one that's 50.0, we have one that's 0, we have one that is, let me fix that so it doesn't cover. We have one that's like 27, we have one that's 23, 41, that should have a 0 on it. And maybe one that's 11, 9, should be 9. So if we average all of those values, it's going to come out to 25.0. And that is where we want to be. But we can also see, just looking at those numbers, that we are very, very imprecise. And so even though everything averages out to be what we're looking for, it's not quite what we're looking for because of how imprecise it is. So it's accurate, not precise. For this one, the precision one, we have a very closely grouped set of numbers, but our numbers are really not that useful to us because they're not accurate. So this would be kind of like if if I ordered something online and I ordered like 23 shirts, maybe, and I wanted a size large in all of them, if I got like 10 smalls, 10 2XLs, and like 3 larges, that would be an accurate but imprecise and also not acceptable order for me to get. And maybe for precise, I would get 23 extra small shirts, which is very precise. They're all closely grouped. They're all the same kind. Not helpful. Not what I wanted. So I hope that's a helpful example for why we want things to be both accurate and precise. But then for an example that was both accurate and precise, we'd have maybe 24.9, 24.8, 5. That is not supposed to be a 50, 25.2, 25.0, 25.1, maybe another 24.9. So that would average out to be just under 25. I think it would come out to something like 24.95. I'm not quite sure. I'm doing that in my head. So it's within 1% because 1% of 25 is going to be 2.25. And so since 0.05, which is our error, is less than 0.25, that would say that we have an accurate result. Although, yes, and because we are ranging from 24.9 to 25.2, so 25.2 minus 24.9. Okay, so that is actually going to be too big. So we're just going to change it to 25.1 because I can manipulate the data. But that's going to come out to 0.2, which again, 0.2 is less than 0.25. So we have an accurate and precise sampling here. Now, if we move on to units. So everything on Earth has a unit, even the things that we don't think have units. So for example, I could have any number of Coke bottles, forgive my art skills, but if I have, let's say, 23 Coke bottles, I guess I really like that number. Well, I happen to have one in front of me. Each bottle, let's get rid of the 23. So each bottle has 240 calories, and that happens to be a unit of energy. 28 fluid ounces, that's a unit of liquids. And we have grams on the back, so 65 grams of sugar. So each one of these numbers has meaning, but none of them would have meaning if we took all of the units off. So if we switched it so that we just had, I believe that was supposed to be a 240. Let me fix that. Yeah, 240. And I'm talking about a Coke bottle. That could mean a lot of different things. I might assume that had something to do with the quantity that was in it. Well, I would probably assume it had quantity with something. It could be the grade. It could be really any number of things. And so we need the units in order to make sense of things. And there's units in everything, including like if I say that I have 4 t-shirts, then my unit is t-shirts. Nothing is unitless. The only thing that's unitless is pure math. And this is chemistry, not pure math. So we're not going to be dealing with any of that. The most important units are what are considered standard, well, they're Système International units, or SI units. It's basically the units that a bunch of people got together and agreed were the most important ones that should be used for science. And that's French, but we just call them SI units. So those would be the kilogram, the meter, second, Kelvin is amperes for currents, and for quantity of something, like if we're just like a number, the mole. And we're not going to get into the mole too much in this video, but it is a unit, sort of. Like I said, we're not going to get into it, but yeah, I'm just going to take it off the list. That might be confusing. But anyways, we have a list of basic SI units. These are the most important ones. The kilogram is kind of a special unit because he's not exactly a base unit. For the most part, we talk about, so this is actually a really good segue into prefixes, but with SI units or metric units in general, we have a base unit and then we use prefixes in order to modify those base units. And because it's the metric system, everything is nice and neat and everything works together in powers of 10. So that means that a kilogram, actually, let me get these units or prefixes down really quick. So we got giga, mega, kilo, deci, centi, and milli. Yeah, so these are the most important ones for our class. There's a couple others depending on, you know, what you're working with that can also be really important and very applicable. But these are the ones that we mostly work with here. So if we start at the bottom, the milligram or milli is times 10. No, I don't like that format. We're gonna actually, so milli is gonna be 0.001. Centi is gonna be 0.01. Deci is 0.1. I should line those up. Kilo is 1,000. Mega is 1 million. And giga is 1 billion. And I am just going to check those really quick to make sure I'm not spreading misinformation in a review video. And I'll pause the recording really quick while I check that. Okay, I'm back. And yes, giga is times a billion and mega is times a million. So what does this mean? Why is that useful to us? How do we use it? So a gram, for example, is approximately, it's a unit of mass. It's approximately the weight of a single paperclip. But if we're measuring, for example, if I want to measure the weight of a single ant, then it doesn't really help me to measure his weight in grams because an ant weighs so much less than a paperclip that the units start to lose meaning. Same thing, if I wanted to measure the weight of a human, then a human is so much larger than, wow, this is not a good looking human, is so much larger than a paperclip that, again, the gram starts to lose meaning. So we needed a way to modify the base units. Well, there were two different ways we could have gone about it. We could have done the imperial system way, which is pounds, feet, slugs, etc., like that, which is just come up with a new unit. But that's kind of messy, and the metric system is all about order and base 10. So instead, we just came up with prefixes. And so for humans, it makes sense to measure things basically in measurements of about 1,000 paper clips. kilograms. That's why when you go to the doctor's office, they measure your weight in kilograms. And then for distances, it makes sense to measure some things in meters, but for other things, for example, the width of a fingernail, that makes more sense in something that's about 1/1000th of a meter. So if you take a look at a ruler, if you happen to have one near you, you'll see that a millimeter is just a much smaller unit. And so it's a lot more useful with smaller things. Basically, we just have these prefixes so that we can make sense of the world around us in a way that is meaningful while using the same basic units. And it's awesome. So we talked just briefly about temperature on the other page, but there are 3 different units of temperature. So there are degrees Fahrenheit, degrees Fahrenheit, degrees Celsius, and Kelvin. So degrees Fahrenheit, I've heard it said this way before, is that Fahrenheit is really good for humans. It's really easy to tell whether something is hot or cold based on the temperature that's given in Fahrenheit. So for a human, 100 degrees is hot and 0 degrees is pretty cold. For water, we use Celsius. And that's actually where it was designed, or where it came from, because 0 degrees Celsius is the freezing point of water, and 100 degrees Celsius, gosh, that should say freeze, and 100 degrees Celsius is the boiling point of water. So it's really nice when you're talking about water to use Celsius, but it doesn't make quite as much sense for humans, and neither of these make perfect sense for science. Of course, nothing really makes perfect sense, but this is where Kelvin came from. So 0 Kelvin corresponds to absolute 0. So that is the point where everything is just so cold that all motion ceases, even just the gentle vibration of your atoms. And we've never been able to get something cold enough to actually reach absolute 0. But that's where it starts, and then it goes up at increments that are the exact same as a degree Celsius. So 1 Kelvin equals 1 degree Celsius, which makes things easy for us because most of our units, for example, calories and degrees Celsius, of course, and there's several others, but those are the only ones I can think of right now, are based off of the Celsius degree. So Kelvin, for science, will preserve that for us and help us maintain all of the formulae and things that have been figured out and used over the years, while giving us a better gold standard to work off of. So how do we convert between them? Well, it turns out that to get from Celsius, well, actually, we'll go backwards. We'll go from Kelvin to Celsius. We're going to add 273.15. We are going to do the exact opposite of that. To get from Celsius to Kelvin, we add. To get from Kelvin to Celsius, we subtract 273.15. And because it's Kelvin, they're not degrees. Once they become Celsius, we get degrees. To get from Fahrenheit to Celsius, we are going to, this one's a little less pretty, but we take 5/9 times by the temperature in degrees Celsius minus 32 is equal to degrees Celsius. Both of these should have degree signs. Okay. So now let's talk about exact versus measured numbers. So for exact numbers, this would be something like if I ask you to get me 2 slices of very artistic bread, then there's no guesswork involved in that. There's either 1, 2, 3, 4, up to like 7.3 billion slices of bread, but that's still an exact number. Well, yeah, like I could count the slices of bread and I could tell you exactly how many there were. I wouldn't round to 7.3 billion if you wanted to know exactly how many there were, but that's just example. But we have exact numbers for things. Like you know how many people are in your family. For me, it's 7. There's no guesswork in that. There are 7 humans. No more, no less. I don't have 2.1 brothers. I have 3 brothers. So that's what an exact number is. Is it something you can count? It's something that is exact. There's no guesswork involved. Now for a measured number, it's different. So we kind of mentioned rulers a little bit ago. Anything that you use a ruler for, anything you use a scale for, anything that you have to measure in any kind of way that you're not just counting, that's going to be a measured number. Thank goodness they gave it such a apt name. So with these measured numbers, there's a lot less certainty that goes into them than with those exact numbers. I should label that. And so with a measured number, the last unit or the last digit of your number is always a guess or it's rounded. For example, if I gave you a grape and a ruler and I asked you to measure the grape and it looked like it was somewhere between 2.3 centimeters and 2.4 centimeters in diameter, you could round, excuse me, sorry. You could round either up or down, depending on where it was at exactly. But that would mean that this number is an estimate. It's not exact. It's not exactly 2.3 centimeters. It's probably 2.35 something centimeters. We can't know. We have limits because of our measurements, because of our human frailties. I wear glasses. I'm blind. Even if that ruler was incredibly precise, I'm not going to know that. I can't see it. So because of this, our measured numbers always have a guesstimate right at the end. That doesn't make them less valid. It doesn't make them less important. But it is important to remember that there is a certain amount of uncertainty involved in measurements. With that, we're going to move into significant figures, which I think are kind of fun. So with significant figure, we're talking about in any given measurement, you have a number of digits. So I'm going to throw some numbers up real quick. Okay, so, and we're going to be talking about the rules that apply to all of these. So with significant figures, we're talking about how many of these numbers am I certain about? And how many of these are basically a guess or unimportant? So if I tell you that I have 6,000 jelly beans, chances are that I do not have exactly 6,000 jelly beans. Probably I have anywhere from like 5,500 to 6,499 jelly beans. And so those last 3 numbers are all going to be an estimate. So actually what we're going to do is we're going to circle the significant. So the 6 is the only significant figure here. So we only have 1. Here, if I tell you I've got 123.2 of something, this is a measured value. That last one was exact, but it was rounded. So 123, that is exact, or that is measured. I know that there's 123. The 0.2, that is an estimate. But your significant figures include all of your measured digits and the first estimated digit. So even though I could say it was 123.245763217, none of those numbers after the 2 mean anything because I didn't measure those. I can say that I estimated them, but I didn't really. I just threw out a bunch of numbers. With 525, we've got 3. Now that we get into zeros, this is where it starts to get fun. So with zeros, there's a couple different things. We have what are called captive zeros. We have leading zeros, trailing zeros, place holding zeros, and captive holding zeros. So with a captive zero, that would be something along the lines of what we have over here. 50046. We'll just leave it as that. So here, since our 2 zeros are sandwiched between a 5 and a 4, we say that they are captive. They cannot escape. They are prisoners here. They're being held against their will. Say what you will about them. They are significant. So if we think about, again, measuring, let's say that this is elephants. I have 50,046 elephants. That is exactly how many I counted. Well, that means that those 2 zeros in there are important. If I take them out, then I'll just have 546. They're holding the place to make sure that, well, they're adding value. They're giving me information. They're telling me something that's important, not just the location of the 5. So that's what makes them significant, is whether or not they're adding value. Leading zeros would be something like 0.00057. So those 3 zeros before the 5 don't actually tell you anything except for the place that the 5 and 7 are going to go. But you didn't measure them. They're zeros, and you can't measure those zeros that are before there. You just know they're not there. Like if I look at my hand, which is, I mean, it's relatively small and human-sized. If I talk about meters, or let's go even further. Let's say that I want to talk about kilometers. This is obviously not to scale. If I want to talk about kilometers, how many kilometers wide is my hand? That's not even a comparison. Like, it doesn't hold any value. There's no meaning. Let me back up. That's not where I was going. It's true, but I can measure my hand in centimeters. And just as an estimate, we're going to say that my outstretched hand is 15 centimeters wide. So using our prefixes, I can convert that to kilometers using what's called a conversion factor. So I know that in 1 kilometer, there are, just a second, I had to do some quick math. Yes, that is the right amount of zeros. Okay, there are 100,000 centimeters, which means that I'm going to take my 15 centimeters, and I want my units to go away. So I want centimeters over centimeters, and they'll cancel just like algebra, just like how you would cancel x's and fractions and whatnot. I get rid of the centimeters, so then I'm going to do 15 over 100,000, which is 0.00015 kilometers. So these zeros, they're not adding any value. They're just telling me where I'm at. Trailing zeros are really similar. This would be something like 500. The zeros after the 5 aren't telling me anything significant. They're just telling me where the 5 goes. Placeholding zeros, on the other hand, would be if I have 500 decimal place. So there, I put the decimal place there because it's my way of showing you via the way that we as a scientific community have decided is valid that those two zeros are significant. I measured them, they matter, they're real. So that's what makes them a placeholding zero, not just a trailing zero. And then with a captive holding zero, wait, no. I sit on a throne of lies. The trailing zero and the placeholding zero switch places. The trailing zeros are the ones that are there with the decimal place. Basically, if there's a decimal place after your zero and there's numbers before your decimal place, then your zeros are significant. If there's no decimal place after your zeros, like this little guy right here, not significant. He doesn't matter. He'd like to believe it, but he doesn't. Captive holding zeros are slightly different. So that would be something like 500.04. So based on the rules before, we might think that these zeros after the 5 are not significant because it's 500. And we might think that this zero, because it's before a 4, is not significant, and it's after the decimal. But because they're all between both the 5 and the 4, they are significant. Okay. Now, we're going to be talking more about these conversion factors. But first, let me throw up. Actually, we are going to be doing something else just before that. We're going to be talking about losing significant figures, which is really easy to do, and you're going to do it a lot. And we've been doing it all semester. But with significant figures, when you add or subtract two numbers, you can only have, or I guess the basis of all of this is that you are only as significant or as precise as your least significant measurement. That's going to be the same basic rule as adding and subtracting as for multiplying or dividing. The way that we do it, however, is just slightly different. So when we're adding or subtracting, the number of significant figures isn't really what we care about. It's number of decimal places. So if I add 1.23 plus 4.0005, my answer is going to be as significant as my least significant input. So it's going to be at 5.23. And I only have 3 significant figures. Versus if I multiply or divide, my number of significant figures is equal to the number of sig figs on my least precise one. So that, for example, is if I do 0.5 times 0.2, I've got one significant figure. Wait, this is a bad example. If I have 0.25 times 0.01, then what I get is I get 0.025. And remember that zero prior to the 2, this guy right here, he is not significant, but this guy has 3 sig figs, and this guy only has 2, so then our answer only has 2, and this guy is a leading zero, so he is not significant. Now we're going to get into scientific notation. Because you might think to yourself, well, if all these zeros are so insignificant, why do we even bother writing them? And the scientists of the world said, you know what? That's right. We should maybe just not do that. So we came up with notation. Now we're going to get into it. And you're going to think maybe this is more trouble than it's worth, but it's not. I mean, I don't know. Anyway, so if we talk about the speed of light, which is usually denoted as c, that is rounding 300 million meters per second. However, this is unwieldy, and while scientists would like to get out there and do lots of hard work and change the world, they do not want to spend all of their time working on things as insignificant as writing a crap ton of zeros. So what we as a scientific community do is we write the first digit, well, all of your significant figures, but the decimal goes after the first digit. We actually only have one significant figure here, so we don't actually get to put a decimal and a zero there because those are not significant, and I would be lying to you if I said they were. I guess if we measured it, then they could be. Anyway, it's going to be 3 times by 10 raised to the power of whatever I have to multiply 3 by to get 300 million. It happens to be 8. So 3 times 10 to the 8 meters per second. Depending on your calculator or anything else that you are able to look at, some people, notation, you might run into something that says 3E8. It means the same thing, but it just means 3 to the times 10 to the 8th, or 300 million meters per second. And we can do this the opposite direction as well. So if I have that ridiculous number, we're going to call it kilograms. Then if I take a look here, and I'll count, I've got 1, 2, 3, 4, 5, 6, 7 decimal places prior to that location that I want it right after the first significant figure. That's 7, I said, yeah. So what we're going to do is we're going to go 5.423 times by 10 to the negative 7th because it is smaller. And so that will make kilograms. Those are just 2 different ways to write the same thing. So the last thing that we're going to talk about today is conversion factors, which honestly is one of my favorite things. So I tutor for a living, so I actually really do like this stuff. I am not full of lies today. But anyways, so for example, we sort of touched on this earlier, but 1 centimeter is equal to, 1 centimeter is equal to 0.01 meters, which is equal to 0.00001 kilometers. The opposite direction is equal to 10 millimeters. But all of these are conversion factors. We set them up as little tables. Well, fractions. Fraction is the word I'm looking for. Ooh, maybe don't do that, Sarah. So I'd set it up like this. 1 kilometer, if that was what I wanted to go with, is equal to 1,000 meters. So a conversion factor is a fancy one. If you remember, back in algebra, used to do things where, for example, let's say that I wanted to take 3/4 and add it to 1/2. And so I would have to multiply 1/2 by 2/2 in order to make the denominators the same. Well, 2/2 simplifies to 1. So I could do that because I wasn't breaking the laws of math. And so I multiply by 1. Well, we do the same thing. I didn't want to do that. We do the same thing in chemistry. I need to stop. We do the exact same thing in chemistry, except instead of numbers, we have units. Mostly, we switch between units like a lot. So what I like to do is I draw these neat little tables. My high school chemistry teacher taught me this. I've never forgotten it. And well, I think it's basically the bee's knees. So, couple things. First off, let's say that I want to go from 100, well, I guess we'll start up here. So let's say that I want to convert 100 kilograms per meter to, let's just go with grams per kilometer. Sure, that works. So what we're going to do here is we're going to start by writing out what we're starting with. 100 kilograms per is a delightful little math word. Also, we just straight up have like a numerator denominator in the unit already, but it's telling us that the meter goes down here. And if there's no unit associated with it, it's a 1. So I would like the kilometers to go away, and I would like the meters to go away. I'm gonna start with kilograms. I would like the kilograms to go away. I'm gonna start with the kilograms. So kilograms. I'm trying to convert to grams. And so how many grams are in 1 kilogram? Well, 1,000. So I just put that up here. And I'm trying to get my grams to kilograms to cancel. So I need 1 to be in the top, 1 to be in the bottom. All right, awesome. Now I have grams. I need to get rid of meters and bring in those kilometers. So we'll do it backwards. 1 meter is equal to 0.001 kilometers. That will cancel out my meters. And what I will be left with is grams per kilometer, which this isn't, you'll probably never use that unit, but it's fine. It's a thing that exists. So anyway, then you're going to multiply. Anything that's in the top, you're multiplying. Anything that's in the bottom, you're going to divide it. So what I'll end up doing is 100 times 1,000 divided by 0.001. And it comes out to what? Grams per kilometer, kilograms per meter. This is, I did something wrong. 1 kilogram, 1,000 grams. Yep, multiply by 1,000, then 1 meter. 1 kilometers. Nope, that is correct. That is accurate math. Okay, it just sounds ridiculous, but I got 1 billion. One more zero. 1 billion grams per kilometer. Okay. Nope, that makes sense. Yep. All right. And that's how I do conversions. So that is everything for the review video. I hope this helped at least one person, and good luck on the final. Bye.